Section 1.2, Domain, Range, and Function Notation. Carrying over from Section 1, we see the graphic of the flask that's going to be filled with water at a constant rate. And next to it, we see the graph that shows the relationship between the time that the water is running for in the unit of measure of seconds and the height of the water in centimeters. And the graph is showing you the relationship. At this point, when we start talking about graphs and the relationship of one variable to another variable, we're going to begin to talk about input and output variables, or in this case what's referred to as the domain and the range. Now let's take a look at how this equation may look. Let's suppose that this graph is represented with y equals x squared. So you put in a value for x and you get out a value for y. So if we pick a value of 1 and we put it into the equation, y equals 1 squared, we get y equals 1. Pick a value of 1, we get out a value of 1. We have the ordered pair 1, 1. We could do the exact same thing, changing y and x to actually represent the variables of time and height. Let's suppose that y, which is height, is h, and x, which is time, is t. These are exactly the same equations, but just now given some specific context. This is relating time to height for this particular flask. At this point, there shouldn't be anything new in what we're discussing. You should have already seen and be very familiar with equations like that, and likewise be very familiar with equations written like that. These are exactly the same thing, just different variables. What is going to be new, the first thing that's going to be new, is talking about domain and range. And in this case, domain refers to all possible values that can be used in the x-axis, or the input. When you put the value for x into your equation and you get back the result, either your y or your height, that refers to the range. The domain is also referred to as your input variable. The range is referred to as your output variable. So the book asks the question, what is the domain of the height function shown in the graph? So that if we've got this function here that's talking about height, what is the possible domain for time? Well, based on this, we can't have time less than 0. And as far as we know, time can run forever. Even if the water's flowing over the top of this, time can run forever. So the possible domain would be basically all numbers starting from 0, all real numbers. And we'll talk about how to write that later. But likewise, if we talk about the range and what the numbers look like for the range, again, it starts at 0. That's the smallest possible value you can have. And it goes from 0. But really, the height can never go any higher than the flask, because at that point the water will start overflowing. So time may run forever, but actually their graph should continue on. Height can never go higher than the height of the flask, whatever that is. We're not sure what it is. So the domain can go from 0 to infinity. The height can go from 0 to, I don't know, 10 centimeters or 1 foot, however tall that flask is. So those are your domain and your range, your input and your output variables. The domain always refers to your x-axis. The output always refers to your range always refers to your y-axis. Now I'm going to erase these and we're going to talk about the second new concept. So at this point, the new item that they're introducing is a new notation system. And let's show it up here with this y equals x squared. The new notation system is called function notation. And basically, all they're doing is taking the range variable, which is y in this case, and replacing it with f of the domain variable, f of x. All that's saying is that what comes after the equal sign is a function that's going to be written in terms of x. That's all it means. So to the right it stays the same. To the left we use f as function, function in terms of x. Now, to show you kind of how it works with this equation down here, again, remember these are equivalent equations. This is just a generic y and x variable. This is a specific height and time variable. So we would use function notation in this case not as f of a generic function, but a function of height in terms of the domain variable time equals t squared. So here we'd read this as f of x equals x squared. Down here we'd read this as the h of t equals t squared. So this new notation may take a little bit to get used to, but from here on out, this is actually going to be probably the more common way that you're going to use them. And it becomes useful, as you'll see in just a minute. But the important thing to note from this notation, that h of t is not the same as h times t. This is not correct. And similarly, f of x is not the same as f times x. That's not what that means. So I'm going to erase a couple things and we'll continue. So now if I have an equation where it says the h of t is equal to t squared, and I want to know what happens when t equals 2, instead of writing t equals 2, I will actually write it as the h of 2 equals, and then I can put in the value of 2 squared and say the h of 2 is equal to 4. So the book gives you examples at the bottom of page 10 where it says h of 0 equals what? So we just think of it in terms of what our basic equation is, or you can look at the graph. 0 represents your domain, your time. So when time is 0, what is h? Well, you can put it in here. T squared is 0, h is 0. So h of 0 equals 0. Similarly, it asks h of 2 equals what? So you can do the same thing. You can take 2, plug it into here. 2 times 2, 2 squared is 4. So h of 2 equals 4. So that's how you can use the notation, the function notation, to be able to quickly keep track of what you're evaluating the equation with. So at this point I'm going to erase this here, and we're going to go to the top of page 11. So the top of page 11, you start with this y equals 1.5x minus 4. And they say, okay, but to write that in function notation, we use the f. In the parentheses, we put the domain variable, and then we put the equation afterward. So this is now the same thing, but one's written in function notation. So given that, we can ask the question, what is f of 2? Nothing any different here from all of the work that you've done before, where you would simply take 1.5, replace x with 2, and do the math. 1.5 times 2 is 3 minus 4. So f of 2 equals negative 1. In this form, you can now see the relationship between the independent, and the dependent variable in a simple notation. So now if we take a look at the problem 1.2a, and we ask, so item 1a is, what are the domain and range of f of x? So remember, domain refers to the input variable, which is your x. So what can x be? So if we think about it, there's really no limitation on what x can be. So basically it can be all real numbers. Similarly, we're going to ask the question, what is the range? Which is your output, which is your y variable. Similarly, there is no limit on what your range is. It's all real numbers. Later you're going to see examples where there are limits on what can actually be put in, but at the moment, for this particular function, f of x equals 1.5x minus 4, there's no limit on your domain and range. I'm going to erase these and we're going to work through a couple of those in 1.2a, 1, a through g.